We're going to look at level triggered D-type flip-flops. Now these are used for controlling delay in a circuit, and we can think of them as the basis for storing data in computer memory, in memory registers. Now a single D-type flip-flop is used to store a single bit, and so it can flip between two states, 1 and 0. If you wish to store more bits, if you wish to store bytes, then you need to have more D-type flip-flops. Now the inputs are controlled by a clock value that changes the state at a regular rate between 0 and 1, and the input data that we are wishing to store, the value that we wish to delay. The output for a level triggered D-type flip-flop can only change when the clock value is 1. So when the clock value is 0, nothing can change. The output can't change. So when we talk about change, we're talking about the value of Q, our output. So just to reiterate, that can only change when our input clock is 1. This is the circuit for a D-type flip-flop. There's a few things to note there. In the way this has been constructed here, it's made of 5 NAND gates. The bottom left one here could be replaced with a NOT gate, but we're choosing to use this approach here. You'll also notice there's a feedback on the rightmost NAND gates. So the output of one NAND gate becomes the input of another NAND gate. Let's have a look now at sort of tracing this through. So if we have a data value of an input of 1 with a clock of 1, then the bottom NAND gate has an output of 0. The top NAND gate will have an output of 0 as well, because you've got 2 1s here. 2 1s for a NAND gate will return you a 0. And the bottom one here, the 0, the data is 1 because it's essentially a NOT gate. The output for that is 0. Then the next NAND gate, you can see the output there is 1 because one of the inputs is 0, and as long as one of the inputs is 0, which it is here, and the other one is 1, well then the output for that is going to be 1. And because the output for the top one here, or the input is 0, because that's 0, then we know the output is going to be 1, because whether you have 0 0 or 0 1, doesn't matter what the other input is, the output is going to be 1. So we know the output for Q is now 1, and because Q is 1, then obviously the value for not Q is 0. So if you can see here, if you have a data value of 1, if you have a clock value of 1, your Q value is also going to be 1. Let's now have a look at if our clock value is now at 0. What happens here is, without going through the circuit in detail, what we end up with is no change, essentially, because we have 2 1s as the outputs of our 2 middle NAND gates here, and so therefore it's just going to stick with the same value of Q and not Q for our outputs. And again, going through this now with 2 inputs of zeros, of data and clock 0, again we can go through this, and again it's not going to change the output in this scenario, so you can work that through for yourself. And then in the final example here, we've got a data of 0, we've got our clock to be 1, and again just going through this really quickly, we've got, if our data is 0 as input, our output for that NAND gate is going to be 1. Effectively, it's a NOT gate. And then we've got 0 and a 1 as an input to that top NAND gate, so that's now going to be 1. We've got 2 1s, we've got the clock value of 1, and we've got the value 1 for that bottom NAND gate. So the output for that is 0. And then again, given that the bottom NAND gate has an output of 0 and is going to an input, then we know that the output of that is going to be a 1 regardless of whatever the other input is. So therefore, then we have Q to be 0 and not Q to be 1. So let's have a look now at how we apply this to a time sequence or changing values of data, and we have our clock cycles, and we can see how this changes against time. So let's pick up our cycle here where the clock is at 1, our data are at 0, and you can see in this case, again, if you work through all the logic, the value of our output Q is now 0. So let's move forward a little bit. So now our clock is at 0, our data is at 1, and our Q still remains at 0, because now, even though our data moved up to 1, we can only change the output of Q when it's been triggered when it's at 1. So when our clock is at 1. So we can only change a value when our clock is at 1. Because the clock's at 0, it can't change the value. Even though the data value has changed, the output still remains the same. Our clock now is at 1. Our data is at 1. And because our clock's at 1, we've got the level triggering there. So our value of Q has now moved up to 1. Our clock now has moved into the 0 part of its cycle, but the data remains at 1, and so our Q also remains at 1 as well. Now our data input now is 0, but our output for Q still remains at 1 because our clock is at 0. Now as our clock changes to 1, our Q now drops to 0 because our input data value is 0. The next stage is our clock is at 0, our data remains at 0, and therefore our output Q will remain at 0, so there's no change in the output. Even though the clock has moved to 1 at this point, our data is still at 0, so therefore our output remains at 0. So going to the end of the sequence, because our input data value now remains at 0 for the remainder of this period, regardless of what the clock is doing, whether it's 0 or 1, our output for Q is going to also remain at 0.